In this video, I'm going to be going through a few practice problems involving cell potentials. And so for this particular problem, or the first problem I have here, I'm going to ask to balance the following skeleton ionic equation in an acidic solution, and then calculate the standard of the manganese 2 plus manganese cell, or half cell, given the fact that the half cell potential of the copper 2 plus copper side is positive 0.34 volts, and the standard cell potential is negative 1.17 volts. And so using this equation that you have, or that I'm giving you, you can see that Mn2 plus aqueous plus copper 2 plus aqueous produces MnO4 minus aqueous in copper solid. And so one thing you should kind of notice just by looking at this is on the left hand side you have no oxygens. On the right hand side you have 4 oxygens. And so somewhere in this new balancing steps, you actually have to figure out how to balance the oxygens. In addition to that, on the left-hand side, you have a manganese 2 plus, a copper 2 plus, and on the right-hand side, you have neutral copper and a MnO4 with only a negative 1 charge. And so that should also kind of stand out as not quite correct, because you can't just have electrons just disappear or go somewhere without actually going somewhere. And so the first thing you need to do whenever you look at these types of problems is the same thing you would if you were just balancing this reaction in an acidic or a basic solution. And so the first thing to do is split this into 2 half reactions. And so very easily you can just kind of figure out which 2 of these, or I guess which 2 out of the 4 complexes belong to one another. And so the Mn2 plus should, again, kind of go along with common sense. The Mn2 plus is going to be converted into the MnO4 minus. The copper 2 plus is going to be converted into the copper solid. And so splitting these into 2 half cell reactions, you can see again the Mn2 plus aqueous is going to convert into the MnO4 minus aqueous. Your copper 2 plus ions are going to be converted into copper solid. And so just by looking at these 2 equations, the way that they're written, you can tell me what is going to be oxidized and what is going to be reduced. I'm not going to explain that information to you. That is something that you should hopefully have a basic understanding from back in like Gen Chem 1. But basically looking at this, your Mn2 plus on the left hand side is going to be converted into Mn7 plus on the right hand side. So please note, 4 oxygens, each of those have 2 minus, and so you're looking at a negative 8 on the oxygens. So in order to end up with a negative 1 overall charge, your manganese has to be a 7 plus on that side. And so going from a 2 plus to a 7 plus, your manganese is going to be oxidized. On the other side of things, you have your copper 2 plus becoming copper solid. And copper solid has an oxidation state of 0. And so you're going from a 2 plus to a 0, or your copper is going to be reduced. And so now we know kind of where we're heading here. We know some electrons are being transferred, and so that's why you have a change in these charges on, like, from the reactant side to the product side. In addition to that, as I mentioned earlier, we have to figure out where these oxygens are coming from. And so the reason why they're not really in this overall equation yet is because this is happening in an acidic solution. And so in order to balance your oxygens, you need to add waters to the other side. And so in this manganese equation, you have 4 oxygens on the right side, meaning that you need to have 4 waters on the left-hand side. And so now we have our oxygens balanced, but in addition to adding oxygens, if you add water, you're also adding hydrogens. And so in order to balance those out, you need to add H pluses to the opposite side of where you added your waters. And so since you added 4 H2Os, you need to add 8 H pluses in order to have your hydrogens balanced out. But because you added H pluses, you have now messed with the charges. And so in order to balance out the charges, you need to add electrons to get the charges on the left-hand side and the right-hand side equal to one another. And so here you have a 2 plus on the left-hand side coming from that manganese 2 plus. On the right side, you have your manganese, or MnO4 minus, and you have 8 H pluses. And so on the right side, you're currently looking at a total of 7 plus. But on the left-hand side, we have 2 plus. And so in order to get both sides equal, you need to add 5 electrons to the product side. And so 5 minuses plus your 1 minus plus your 8 pluses, you end up with 6 plus on the, 2 plus on the right hand side as well as the left hand side. So the copper reaction is really easy to balance, mainly because there is no oxygens or hydrogens. Copper is already balanced. There's one copper on the left and one copper on the right. So the only thing that you need to do here is balance the charges. So, as I've kind of mentioned many times since Gen Chem 1, do not try to balance charges by adding elements, because you just mess everything up and you have to do a lot more balancing. So in order to balance charges, all you need to do is add electrons to the correct side. And so in this case, you need to add 2 electrons to the reactant side, because it's going to have 2 electrons plus your copper 2 plus to give you your copper solid. And the last step to take before you start throwing all these things together is to make sure that the number of electrons is equal on both equations. And so here on the oxidation half reaction or half cell, you have 5 electrons. On the reduction side, you have 2 electrons. And so in order to make these things equal, you actually have to do a little bit of cross multiplication here, or multiply the entire first reaction by 2 and the entire second reaction by 5. And so once you kind of put these things together and do the cross multiplication appropriately, make sure to add everything together, the correct values, after you've already multiplied the entire reactions and coefficients. And so in this overall reaction, you have 2 times your 4 waters, or 8 H2Os. You have 2 Mn2 pluses, and you have 5 times your 2 electrons to get 10 electrons, and 5 times your Cu2 plus. On the product side, you have 2 MnO4 minuses, you have 2 times your 8 hydrogen or H pluses, and so you have 16 H pluses, and 2 times 5 electrons. And the bottom half is you have 5 of your coppers coming from your reduction half cell. And so here you should notice the fact that 10 of our electrons become 10 of our electrons. So we can very easily just cancel those out because they did not do too much. And so here, once you cancel those out, waters, you don't have waters on both sides. Manganese, same kind of deal as like the very initial equation. And copper as well. And so here, the only thing that can cancel out is going to be your electrons. And so your balanced equation in an acidic solution is 8 H2O liquid plus Mn2 plus aqueous plus, sorry, that should be a 2 sitting right there. I missed my count. So 2 Mn2 pluses plus 5 Cu2 pluses gives you 2 MnO4 minus plus 5 Cu plus 16 H pluses. And so here again, this is if you have an acidic solution. If for some reason the question asks about the basic solution, because you have 16 H pluses on that right side, you would need to add 16 OH minuses to both sides and then cancel out whatever waters are left over there. So the second half of this equation or problem is asking for you to solve for the half cell potential of the manganese 2 plus manganese. And so when we look at the cell potentials of these half cells, you just need to realize that the one equation, only one equation that you need to know for this portion of the chapter at least, is that E cell is going to be equal to the E of the cathode minus E of the anode. And if you have an issue remembering that, then remember the other portion of the standard cell potential is going to be the standard potential of the reduction side minus the standard potential of the oxidation side. And so in my slides on Blackboard, I say something about a red cat and an ox, or whichever way will help you out to remember whichever one these are. Another way to remember this is redox. It's just the redox reactions, and so it's going to be the read minus the ox. And so here we are given the standard cell potential of negative 1.17. We are given the standard half cell potential, the copper 2 plus copper, of positive 0.34. And so all we really need to do is just plug it into this equation, making sure that your signs stay appropriate here. And so here, once you have the two equations, all you really need to do is kind of add to the other side and solve for your standard potential of the manganese 2 plus manganese. So in this situation, your standard half potential of the manganese 2 plus manganese half cell part is positive 1.51. That standard potential of the copper 2 plus copper half cell is positive 0.34 volts. And because the way that it is written, with the manganese 2 plus and the copper 2 plus as reactants, and the manganese O4 minus and the copper solid as products, again, it has to fall into this form. If we were to flip this around, then everything else would be slightly different just because we're looking at a different reduction-oxidation reaction. But the way that this is written, it's telling you that this standard potential is going to, again, be positive 1.51, and this is actually going to be not a very good actual cell, because, again, for a decent, effective cell, you want this E cell to be a positive number, not a negative number. So, let's try to take a look at how are we supposed to tell if these things are spontaneous or not. And so the way that this equation is written, sodium plus iron gives you sodium solid plus iron 2 plus. And so when we kind of go through and do this, I don't give you too much information, mainly because if I were to give you a problem like this on the test or on the homework, we would either give you a table with all these standard potentials, or I would tell you the standard potential somewhere in here. I will give you the values later on in a few seconds here, but just keep in mind, I do not expect you to memorize all of these potentials. I want you to be kind of familiar with the more reactive metals are more reactive, but I don't really expect you to memorize each one of these individual values. The first thing you need to do is, if we're talking about spontaneous versus non-spontaneous, we need to kind of keep in mind what I just said with that previous problem. Your cell potential should be positive if you are going to have an effective spontaneous reaction. If it is negative, then again, things won't actually go the way they're supposed to. And so we kind of go through and look at this. First thing you need to ask yourself is what is being reduced and what is being oxidized. And so if we look at sodium going from the left-hand side to the right-hand side, we're looking at sodium plus becomes sodium solid. Sodium solid has an oxidation state of 0, so it's going from a +1 to a 0, or it is being reduced. Iron, on the other hand, starts off as iron solid, which has an oxidation state of 0, and becomes iron 2 plus, or it's being oxidized. And so in addition to that, we know some half-cell reactions. And so here, when we kind of take a look at this, we have sodium plus an electron gives us sodium, and our iron 2 plus aqueous plus 2 electrons give us our iron solid. These are the values that I told you that you are not expected to memorize, and these will be given to you on the exam if a question like this arises. And so the main thing that you need to understand here is, even if you were to flip these equations around, the E's, like standard potential, those won't change, because again, these are still going to be the same relationship of adding electrons, taking electrons away. The thing you need to pay attention to is write them down the way they're being reduced or oxidized. And the main reason why I just did that previous step is because we're going to use that same equation we just saw, or the standard cell potential is going to be equal to the standard potential of the cathode minus the standard potential of the anode, or the standard potential of the thing being reduced minus the standard potential of the thing being oxidized. And so for this one, when we look at this, we have the standard potential of the cell is going to be negative 2.71 volts, because again, that's coming from the cathode, or the thing that's being reduced, minus the negative 0.44 coming from the iron, which is being oxidized, or is the thing that's sitting at the anode portion of the cell. And so when you look at this value is negative. As I stated just a little while ago, if your E, or if your standard cell potential is negative, that means this reaction is non-spontaneous. If you want a spontaneous reaction, you need to have a positive cell potential. So, how can we make this reaction spontaneous? And so if I have a reaction written in one way and it is non-spontaneous, reversing that reaction will make that a spontaneous reaction. And so for this case, if I switch my sodium plus and my iron with my sodium solid and my iron 2 plus, or if I switch the entire reaction around, now your sodium is now being oxidized. Your sodium is going from a 0 to a positive 1. Your iron is now being reduced. It's going from a 2 plus to a 0. And so in this case, using the same equation, but now again, kind of flipping things around, the values don't change. Just the order in which the values appear in this reaction do. And so here again, your cathode is still where you're having reduction. The iron in this case is being reduced instead of being oxidized as it was previously. Your sodium is now being oxidized instead of reduced. And so here you're just going to be switching the order in which you plug these equations into your subtraction problem. If you rewrite it like this, the sodium going from a 0 to a positive 1, and your iron going from a 2 plus to a 0, this is a spontaneous reaction. Because when you plug all these equations in, variables into the equation, this comes out as positive 2.27 volts. So remember, the main key thing here is figure out what is being reduced, what is being oxidized, and subtract them in the correct order. Make sure it's always going to be the reduced minus the oxidized. And last but not least, let's look at this much more enjoyable reaction problem here. And so I want you to calculate the cell potential of a galvanic cell composed of cadmium, cadmium 2 plus, and zinc, zinc 2 plus half cells at 25 degrees Celsius. And I give you the concentration of your cadmium 2 plus ions is 0.02 molarity, and the concentrations of your zinc 2 plus ions is 0.01 molarity. And so one thing you should kind of notice here is I am asking about cell potential. Please notice nowhere in that problem did I say anything about standard. And so remember, standard cell potential is different than cell potential. The same idea that standard enthalpy is different than enthalpy of an individual reaction at a different temperature. And so in these cases, you cannot just use your standard potentials anymore in order to do some subtraction, because it's not really going to qualify. Because now you're looking at something that is at a different temperature. You're looking at concentrations that are not at standard concentrations. And so in this case, you have to use a completely different equation that actually relates your standard potential that you can solve for and your regular old everyday cell potential that you're going to be actually asked for here. Additionally, as I mentioned in one of my previous videos, anytime you see concentration or you see partial pressure, the main thing that you should immediately think of is Q's or K's. Because remember, Q, or your quotient ratio, is nothing more than the ratio of your concentrations of your products over reactants. In this case, I'm not asking about something at equilibrium, so K is already kind of off the plate. And so, the only equation that I've given to you in your slides that actually relates your standard cell potential and includes Q, luckily, is going to be your cell potential is equal to the standard cell potential minus RT over NF times the natural log of Q. R is still going to be our gas constant. T is temperature, N is actually the number of electrons that is going to be transported here, and F is Faraday's constant. And so the other thing that we have, because I'm telling you specifically what half cells we're using, we can actually, again, either determine and or look up our half cell reactions. And so because I'm telling you that we have cadmium 2 plus and zinc 2 plus, we know in order for cadmium 2 plus to become cadmium solid, it has to gain 2 electrons. Same deal with zinc. If we know a zinc 2 plus is going to become a zinc solid, it has to gain 2 electrons. And either by looking them up on a table that we're going to give you, or if I give them to you on the exam, you can determine that the standard potential of your cadmium half cell is going to be negative 0.403 volts. And your cell potential, standard cell potential of your zinc half cell is going to be negative 0.760 volts. So, I know that's a lot to infer just from the very beginning, but it's going to be the same exact material as in the past. Figure out what your half cells are. If given, or if you can, look up what the standard half cells are. In this case, you can't just use those in order to figure out the final answer, because I'm not asking about things in standard form. I want to know the cell potential at a random temperature with random concentrations. But again, let me kind of go through and look at this. In order for this cell to even be useful, as I've stated from the previous 2 problems, your standard cell potential needs to be greater than 0 volts. If it's less than 0 volts, that means that this thing is non-spontaneous. If you have a battery that you actually have to crank in order for the battery to work, that is a horrible battery. And so in this case, again, if you want to have an effective battery that works by, again, spontaneous means, or by you plugging the battery in and it turns on things, then again, you need to have your standard cell potential greater than 0. And so the main reason why I bring that up is because you can tell from the way that this is written which one of these has to be reduced and which one has to be oxidized. And so given your standard potentials for the half cells, you just need to look at those two values, figure out which one subtracted from the other one is going to give you a positive number. If you subtract the two and it gives you a negative number, that's not the one you want to use. And so in this situation, we know that negative 0.403 minus negative 0.760 is going to be a positive number. If you have negative 0.760 minus your 0.403, that's still not going to be enough there. And so in this case, we know that our cadmium needs to be reduced and our zinc needs to be oxidized. And so when we kind of write this out in this form, we have our cadmium 2 plus being reduced to cadmium solid. We have our zinc solid being oxidized into our zinc 2 plus. And so the way that we can kind of go through and look at this is, again, we know that our negative 0.403 minus our negative 0.760 is going to give us a positive 0.357. As I stated just a few seconds ago, if we were to switch these things around, if we were to write out a reaction as cadmium solid plus zinc 2 plus gives us the cadmium 2 plus plus our zinc solid, our cathode and our anode would be switched. And if so, that equation would be written out as negative 0.760 minus your negative 0.403, which would still be a negative value. You need to have a positive cell potential, standard cell potential, in order for this to be an effective battery. And so now we know our E cell. R is never going to change. Temperature was given to you. N, we'll solve that for a second. It takes about like half of a second to do so. F, it's a constant. I'll either give that to you or I'll give you some form that you need to know. So the last thing we need to solve for here, the unknown thing, is going to be Q. Q hasn't changed in definition. Q is still going to be your products divided by your reactants. But the great thing about this problem, the way it's set up, is you usually leave out pure liquids and solids out of your quotient equation. And so here, cadmium solid is going to be left out. Zinc solid is going to be left out. And so your Q simply becomes your zinc ion concentration over your cadmium ion concentration. And please note, I am writing this as product over reactants, which if you have this thing written the opposite direction will mess this whole equation up, or this Q up. And so using the given concentrations for your cadmium and your zinc is 0.01 molarity. Again, there is no coefficients required in this. It's all just a 1 to 1 to 1 to 1 equation. And so you just have the same concentration as your zinc. Same deal with the cadmium. Cadmium is given to you as the 0.02, and so your Q becomes 0.5. And so now we know our E cell, standard E cell. We know our Q. The last thing we need to kind of figure out is N. And so N, as I mentioned, is the number of electrons being transported. Here I have cadmium 2 plus 2 electrons. I also have zinc 2 plus 2 electrons. So the number of electrons is 2. And so for this, you just need to plug all of this fun information into our long equation, or your E cell is positive 0.357 volts. R is your gas law constant, or 8.3145 joules per mole Kelvin. Our temperature is going to be 25 degrees Celsius plus 273.15 in order to convert it into Kelvin. As I mentioned, we have 2 moles of electrons being transported, and Faraday's constant is 9.65 times 10 to the 4th coulombs per moles of electron. Last but not least, take the natural log of your Q, or natural log of 0.5, and I end up getting with potential, or cell potential, as 0.366 volts. Hopefully this helps you all out, and good luck on the exam.